Looking back, even fairly good students, when they have obtained the solution of the problem and writing them down neatly the argument, shut their books and look for something else. Doing so, they miss an important and instructive phase of their work. By looking back at the completed solution, by reconsidering and re-examining the result and path that led to it, they could consolidate their knowledge and develop their ability to solve problems. A good teacher should understand and impress on his student the view that no problem where is completely exhausted. There remains always something to do. With a sufficient study and penetration, we would improve any solution. We could improve any solution, and in any case, we can always improve our understanding of the solution. The student has now carried through his plan. He has written down the solution, checking each step. Thus, he should have good reason to believe that his solution is correct. Nevertheless, errors are always possible, especially if the argument is long and involved. Hence, verification are desirable, especially if there is some rapid and intuitive procedure to test either the result or argument. It should not be overlooked. Can you check the result? Can you check the argument? In order to convince ourselves of our presence or of our quality of an object, we like to see and to touch it. And as we prefer perceptions through two different senses, so we prefer conviction by two different proofs. Can you derive the result differently? Can you derive the result differently? So in other words, can you make the solution in another way that you haven't tried? We prefer, of course, a short and intuitive argument to a long and heavy one. Can you see it at a glance? One of the first and foremost duties of the teacher is not to give his students the impression that a mathematical problem have a little connection with each other, and no connection at all with anything else. We have natural opportunity to investigate the connections of the problem when looking back at its solution. When looking back at its solution, the student will find looking back at the solution really interesting if they have made an honest effort and have the consciousness of having done well. Then they are eager to see what else they could accomplish with that effort and how they could do equally well another time. The teacher should encourage a student to imagine cases in which they could utilize again the procedure used or apply the result obtained. Can you use the result or the method for some other problem? Example. In section 12, the student finally obtains the solution. If the three edges of the rectangular parallelogram issued from the same corner are A, B, C, the diagonal is root A square plus B square plus C square. Sure. Can you check the result? The teacher cannot expect a good answer to this question from the inexperienced students. The students, however, should acquire fairly early the experience that programs in letters have a great advantage over purely numerical problems. If the problem is given in letters, its result is accessible to several tests to which a problem in number is not susceptible at all. Our example, although fairly simple, is sufficient to show this. The teacher can ask several questions about the result which the student may readily answer with yes, but answers no would not show a serious flaw in the result. Serious flaw, so fault in the result. Did you use all the data? Do all the data ABC appear in your formula for the diagonal? Length, width, and height plays the same role in our question. Our problem is symmetric with respect to ABC. Is the expression you obtained for the diagonal system symmetric in ABC? So is the expression you obtained for the diagonal symmetric in ABC? Does it remain unchanged when ABC are interchanged? Our problem is a problem of the solid geometry. To find the diagonal of the parallel pipe with a given dimension ABC. Our problem is analogous to the problem of the plane geometry. To find the diagonal of the rectangle with a given dimensions A, B, is a result of our solid problem analogous to the result of the plane problem? Is the result of our solid problem analogous to the result of the plane problem? If the height C decreases and finally vanishes, the parallel pipe become a parallelogram. If you put C equals 0 in your formula, do you obtain the correct formula for the diagonal of the rectangular parallelogram? If the height C increases, the diagonal increases. Does your formula show this? If all three measures A, B, C of the parallel pipe indicates in the same proportion, the diagonal also increases in the same proportion. If in your formula you substitute 12A, 12B, 12C for A, B, C respectively, the expression of the diagonal owing to this substitution should also be multiplied by 12. Is that so? If A, B, C are measured in the feet, your formula gives a diagonal measured in the feet too. But if you change all the measure into the inches, the formula should remain correct. Is that so? The two last questions are essentially equivalent. See test by dimension. These questions have several good effects. First, an intelligent student cannot help being impressed by the fact that a formula passes so many tests. He was convinced before that the formula is correct because he derived it carefully. But now he is more convinced, and his gain in the confidence comes from the different source. It is due to the sort of the experimental evidence. It is due to the sort of the experimental evidence. Then, thanks to the foregoing questions, the detail of the formula acquire new significance and are linked up with the various facts. The formula has therefore a better chance of being remembered. The formula has therefore a better chance of being remembered. The knowledge of the student is consolidated. Finally, these questions can be easily transferred to similar problems. After some experience with similar problems, an intelligent student may perceive the underlying general ideas, use of all relevant data, variation of the data, symmetry, analogy. If he gets into the habit of directing his attention to such a point, his ability to solve problems may definitely profit. Yes. Can you check the arguments? To recheck the arguments step by step may be necessary in the difficult and important cases. Usually, it is enough to pick out touchy points for rechecking. If in our case, it may be advisable to discuss retrospectively the question which was less advisable to discuss as the solution was not yet attained. Can you prove that a triangle with side XYC is a right triangle? Can you use the result or the method for some other problem? With a little encouragement and after one or two examples, the student easily finds the application which consists essentially in giving some concrete interpretation to the abstract mathematical elements of the problem. The teacher himself used such a concrete interpretation as he took the room in which the discussion takes place for the parallel pipe of the problem. Adult student may propose as an application to calculate the diagonal of the cafeteria instead of the diagonal of the classroom. If the student do not volunteer more imaginative remarks, the teacher himself may put a slightly different problem. For instance, being given the length of the Y's and the height of the rectangular parallel pipe, find the distance of the center from the one of the corners. The student may use the result of the problem they just solved, observing that the distance required is 1/2 of the diagonal they just calculated, or they may use the method introducing a suitable right triangle. The matter alternative is less obvious and somewhat more clumsy in the present case. After this application, the teacher may discuss the configuration of the 4 diagonals of the parallel pipe and the 6 pyramids of which the 6 faces are the bases, the center, the common vertex, and the semi-diagonals, the lateral edges. When the geometric imagination of the student is sufficiently enlivened, the teacher should come back to this question: can you use the result or the method for the other problem? Now, there is a better chance that the student may find some more interesting collective interpretation. For instance, the following. In the center of the flat rectangular top of the building, which is 21 yards long and 16 yards wide, a flagpole is to be erected 8 yards high. To support the pole, we need 4 equal cables. The cables should start from the same point 2 yards under the top of the pole and at the 4 corners of the top of the building. How long is each cable? The student may use the method of the problem they solved in detail, introducing a right triangle in the vertical plane and another one in the horizontal plane. Or they may use the result, imagining a rectangular parallel pipe of which the diagonal X is one of the 4 cables, and the edges are A equal 10.5, B equal 8, C equal 6. By straightforward application of the formula, X equal 14.5. For more example, can you see the result? Can you see the result? Yes, thank you.